So dear students, welcome back. So in today's lecture, we will be discussing about vibration rotation spectra of a diatomic molecule or the diatomic vibrating rotator. तो आज हम डिस्कस करेंगे about the combination of what are the effect of the combination of vibrational transaction and rotational transaction on the spectrum of a molecule. So far we have discussed about the rotational spectrum as well as the vibrational spectrum of individual rigid as well as non-rigid diatomic molecule, and we have seen how the transactions are affecting the spectrum of molecules, or how the rotational and vibrational spectrum of the molecules we can obtain, and what kind of information we can get from that particular spectra. Now, in our last lecture, we were discussing about the vibrational spectrum, and we saw that by the absorption of this radiation in IR region, the vibrational transaction occurs, due to which we get different types of spectrum due to the vibration of the bonds. Now, here the case is when the radiation energy is absorbed in the IR region. What we have seen in case of our vibrational spectrum is that by the absorption of radiation in IR region, the transaction between two individual, first or second or first and third, the transaction occurs between these respective energy levels. So अब यहाँ पे क्या होता है कि जब आपका IR radiation absorb करता है molecule, so this IR radiation brings simultaneous change in both the rotational as well as and vibrational energies of the molecule. So this is important. The absorption of electromagnetic radiation in the IR region brings about simultaneous change both in the rotational as well as vibrational energies of the molecule. Now we will see what are the effect of these both simultaneous change, or is there any effect on the spectrum of the molecules or not. So this kind of spectrum is known as vibration rotation spectrum. It means the spectrum is arising due to the change in the vibrational as well as rotational energy of that molecule. I means कि आज हम देखेंगे कि जो अभी तक हमने डिस्कस किया था, सबसे पहले हमने डिस्कस किया था रोटेशनल स्पेक्ट्रा के बारे में, बोथ रिजिड एज वेल एज नॉन रिजिड मॉलिक्यूल के बारे में. इसके बाद हमने डिस्कस किया अबाउट द वाइब्रेशनल स्पेक्ट्रम ऑफ एदर ए रिजिड और ए नॉन रिजिड रोटेटर. इसके बाद अब हम देखेंगे इन दोनों को कंबाइन करके कि आपका आईआर रेडिएशन जो है दोनों वाइब्रेशनल एज वेल एज रोटेशनल एनर्जी लेवल्स में ये क्या करता है, चेंज प्रोड्यूस करते हैं. नाउ वी विल सी व्हाट आर द इफेक्ट ऑफ दिस चेंजिंग ऑन द स्पेक्ट्रम. Beside this, these vibrational as well as rotational changes are considered as independent event. So the rotational as well as vibrational changes are considered as independent. Events. It means that there is no interaction between the vibrational and the rotational energies, or we can say the change in the energy of the vibrational and the rotational energy level. So दो चीज यहाँ पे आपको याद रखना है कि एक तो IR रेडिएशन में एब्जॉर्प्शन की वजह से आपकी दोनों रोटेशनल एज वेल एज वाइब्रेशनल एनर्जी ऑफ द मॉलिक्यूल चेंजेस. The second assumption we are taking here is that the rotational and the vibrational energy change are quite independent. It means there is no interaction between the change in the rotational and the vibrational energy levels. So what we can say here is that the total change in the energy of that molecule is or will be the algebraic sum of the rotational and the vibrational energy changes. So if these two are quite independent, that what we get here is that the net energy change is the algebraic sum of rotational and vibrational energy changes. So इसका मतलब क्या है कि आपकी मॉलिक्यूल का जो टोटल एनर्जी होगा that will be equal to the change in the vibrational and the change in the rotational energy level. So I mean the total energy of this system will be equal to the sum of the rotational and vibrational energy changes. So I can write here is E total. E total means that the total energy of the system will be equal to change in the rotational energy level, that is E rotation, plus change in the vibrational energy levels. So this equation I can write here is that the total energy of the system will be equal to the algebraic sum of the energy change in rotation and as well as vibrational energy levels. And this energy we can express in joules. Now, in spectroscopy, we are mainly dealing with our wave numbers. So let me change this into wave number units. So I can write here is epsilon total is equal to epsilon rotation plus epsilon vibration, and this will be in your centimeter inverse. So I can get here is an equation where the total energy of the system will be equal to change in the rotational energy level and the vibrational energy level. So now here we have to see what are the total change in the energy of the particular rigid or non-rigid diatomic molecule. Now what I will do is I will substitute the value of energy of respective rotation and vibrational energy levels, which we already discussed it in our earlier lecture. So I am writing here the energy of a rotational diatomic molecule, which is equal to B J into J plus 1, which we were already known during the discussion of the rotational energy level. And along with this, I have the distortion constant, that is d J square J plus 1 whole square, plus I have some other terms, that is for higher energy terms, that is Hj cube into J plus 1 whole cube and so on. So this is the equation for a rotational diatomic molecule. या I can say ये हमारे पास energy equation है एक diatomic rotating molecule के लिए. Similarly, in our last lecture, we got the equation for the energy of a vibrating molecule, that is epsilon या E vibration is equal to किसके बराबर होंगे, that is mu plus या V plus 1 by 2 omega E bar minus V plus 1 by 2 square omega E bar XE. So I have two equations. One is the energy equation for the rotating diatomic molecules, and another is the equation for a vibrating diatomic molecule. Now, what I will do here is I will calculate the total energy of this system, which will be equal to this plus this. So I can write here is delta E will be equal to, that is, or I can say delta E means epsilon total, or I can write it as epsilon J V, that is the total energy of the vibration and rotation Yeah, I can say the change in the energy of the rotational energy levels and the vibrational energy levels. So let me substitute this equation into this equation. What I will get here is, and for our convenience, we know that the value of the distortion constant is very less. And as we go further to the higher term, the energy will further, this term will further be negligible. And for our convenience, we will consider it as negligible. So I am not writing this part. I am only concerning with this part of the rotating diatomic molecules. So the total energy of the system will be B J into J plus 1, then plus V plus 1 by 2 omega E bar minus V plus 1 by 2 whole square omega E bar XE. So this is the equation for a total energy of a vibrating, rotating diatomic molecule. So we have an equation here, which is the total sum of the energy of, that is the vibration as well as rotation energy. Now, what I will do here is I can apply the selection rules here, and from which we will get an equation for a vibrating rotating rotator, or I can say vibration rotation spectrum of a diatomic molecule. So what I can do here is that if we have to calculate the energy difference, the total energy delta E will be equal to E final minus E initial. It means higher energy level minus initial energy level. To do that, what I will do here is, so I will take one higher energy levels, that is delta E is equal to E J. I will take the higher energy levels as J dash, V is equal to 1 minus E J double dash, V is equal to 0. So I will take the difference between the two energy levels, and also I will apply here the selection rule. So the selection rule here is, the combination of both the selection rule for the vibrational and the rotational spectrum. So for a rotational spectrum, delta V should be plus minus 1, plus minus 2, and so on. But for a rotational diatomic molecule, delta should be plus minus 1. So before calculating this equation, I will draw the energy levels of a diatomic molecule. So let me draw the energy levels of your rotating, vibrating diatomic molecule. So first I will draw the vibrational energy levels. And we know that the energy gap between two vibrational energy levels are equal, which we have already discussed in our earlier lecture. So this one is our vibrational energy levels. I will take the gap between these two. The first energy level V is equal to 0, and this is V is equal to 1. So this is our first energy level, and this is our second energy level. And we also know that there are number of rotational energy levels in between a single vibrational energy level. So let me draw here the rotational energy level. So a vibrational energy level consists of a number of rotational energy levels. So यहाँ पे जो ब्लैक कलर से ड्रॉ कर रहे हैं वो हमारे पास रोटेशनल एनर्जी लेवल्स है, और हमें पता है रोटेशनल एनर्जी के बीच में जो गैप होता है वो यूनिफॉर्म नहीं रहता है. जैसे ही आपका J का वैल्यू बढ़ता जाता है तो द गैप बिटवीन द एनर्जी लेवल्स were further increases. So let me draw in this also. So first rotational, second rotational energy level, third, and so on forth. So the red color line are our vibrational energy levels, and black colors are our rotational energy levels. And let me represent here the higher energy levels is J dash and the lower energy levels is J double dash. So these plaque are our rotational 0, 1, 2, 3, J0, J1, J2, J3. Similarly, J0, J1, J2, J3. These are the ground state and these are the first excited state. So these इस तरह हम क्या कर सकते हैं, वाइब्रेशनल और रोटेशनल एनर्जी लेवल्स को ड्रॉ कर सकते हैं। और ये ऑलरेडी आपको पता है कि एक वाइब्रेशनल एनर्जी के अंदर बहुत सारे रोटेशनल एनर्जी लेवल्स एग्जिस्ट करते हैं। दैट्स व्हाई वी हैव ड्रॉन हियर ए नंबर ऑफ रोटेशनल एनर्जी लेवल्स इन बिटवीन सिंगल वाइब्रेशनल एनर्जी levels. Now what I will do is I am applying these selection rules here. The selection rules for vibrational cross-section is delta V is equal to plus minus 1, plus minus 2, plus minus 3. And for a rotational, rotating diatomic molecule, the selection rule will be only delta J is equal to plus minus 1. It means that the transaction can occur in between two energy levels. So these are the energy levels we can draw for a rotating, vibrating diatomic molecule. Now I will apply the selection rules and I will calculate this. That is the energy of the transaction when your molecules are when your molecules are undergoing transaction from one energy levels to another. That is lower energy levels to higher energy levels. So what I will do here is I will subtract the higher energy, lower energy levels from your higher energy levels. We have drawn here the higher energy levels is J dash and lower energy levels is J double dash. So if I substitute this value of this in this equation, what I will get here is that the delta E is equal to B, higher energy levels. We will substitute this J as J dash because the higher energy level we have represented here is J dash. So what will be the equation is Bj, J means J dash into J dash plus 1. Yeah. Then we have substituted this V as 1. So in place of V, that is the first rotational vibrational quantum number. In place of V, I will write 1 plus 1 by 2 because I have written here is V is equal to 1 to V is equal to 0. That is transaction taking place from your ground first vibrational energy levels to your first excited energy levels. And here I have omega E bar. Along with this, I have V plus 1 by 2 square, that is 1 plus 1 by 2 square, and omega E bar XE. So these are the total for our first vibrational state. We have to subtract this from our ground state, that is V is equal to 0. So I have to subtract this from this B J double dash plus 1, that is the lower energy level, plus again I am substituting this in this case V is equal to 0 because we are taking from first the ground state to first vibrational state. So the equation will be like 0 plus 1 by 2, it will be 1 by 2 omega E bar minus again here 0 plus 1 by 2 square, that is minus 1 by 4 omega E bar XE. So this is the equation. Let me solve this equation. If I solve this equation, what will happen here is what I will do, I will try to solve these terms first. So I will write Bj dash into J dash plus 1 as such. I will solve this, that is a 2 1 2 plus 1 3 by 2 omega E bar minus 2 1 2 plus 1 3 3 3 9, that will be 9 by 4 omega E bar XE minus this side we have nothing to do as of now, Bj dash J double dash plus 1 plus 1 by 2 omega E. No, here it is minus. Is this minus? So again here it is minus 1 by 2 omega E minus 1 by 4 omega E XE. So this is the equation. Further solving this equation, we can get let me combine the similar terms here. Similar term means let me combine 3 by 2 omega e and 1 by 2 omega e and 9 by 4 omega xe and 1 by 4 omega xe. By doing this, what I will get here is, let me combine these two, 3 by 2 omega e bar minus 1 by 2 omega e bar minus 9 by 4 omega e bar xe plus 1 by 4 minus plus omega e bar xe. And what I will remain here is b j dash b j dash j dash plus 1 minus bj double dash j double dash plus 1. Then further solving this, we have here 2 and 2 dash same. Then we have 3 minus 1, 2 by 2. So 2 by 2 omega e bar minus here is 4, 4 same. So in the denominator, we will 4, 9 minus 9 plus 1, that will be your 8 omega e bar xe plus b j dash plus 1 minus b j double dash plus 1. So this is the equation. So here again I can cancel this 2 and 2, 4 and 2, 8. The equation will become omega e bar minus 2 omega e bar xe plus, let me take b as common between these two. So the equation will be like this: b j, and multiplying these two, let me first do this, j dash plus 1 minus j double dash plus 1. Further solving this equation, what I will get here is omega e bar minus 2 omega e bar xe plus b, and I am multiplying these two. What I will get here is j dash into j dash. It will be j dash square plus j dash minus j double dash square plus, that is plus minus minus, and it will be j double dash. So this is the equation. Now, what I will do is I will substitute these two terms, omega e minus 2 omega e xe. Usually we have one equation like this, which is the fundamental absorption band, the equation for the fundamental absorption. I will substitute these two with your omega naught bar. So I will write omega naught bar in place of these two, plus then again I will combine the similar terms, that is the square terms, that is b. What I will do is I will combine the square terms, that is j1 square minus j dash square minus j double dash square plus j dash and this one minus j double dash. So further solving this equation, what we can get here is I can write omega naught bar as such. Here I can expand this equation as a square minus b square, which is equal to a minus b into a plus b. So b, we can write b as such, then I can write j dash minus j double dash into j dash plus j double dash plus, we can write it as such, j dash minus j double dash. Okay, so again let me take this j dash j double dash as common. So what I will remain here is b j dash minus j double dash. B is already, we have taken it common, j dash plus j double dash, and here we will get 1. So this is the equation. We have another equation, that is our the energy, that is delta E, is equal to omega naught bar plus B J dash minus J double dash into J dash plus J double dash plus 1. So let's type this as equation number 2. Now, what are the significance of this equation here is, so by taking this B to be identical in both our lower energy as well as upper vibrational state is a direct consequence of our Born-oppenheimer approximation. What we mean by Born-oppenheimer approximation is that both the vibration as well as rotational energies are quite independent. This is the approximation of Born-oppenheimer. The vibrational and the rotational energies can exist as quite independent state, which means that the rotation unaffected the vibration. It means when your molecules are absorbing the infrared radiation, both the rotational as well as vibrational energy change take place, but the change are quite independent. There is no relation between the vibrational and the rotational energy levels. So this is what our Born-oppenheimer approximation. Now here I can have two cases. So now we have two cases. Case number 1. Let's see case number 1. What is our case number 1? What we can do here is, now we have a selection rule where delta J is equal to plus minus 1. That is the selection rule for a vibrational transaction. So case number 1, I will consider delta J is equal to plus 1. Means our transactions are taking place from J is equal to 0 to J is equal to 1. So this is the case when your selection rule says the change in the rotational quantum number is plus 1. Plus 1 means that your molecules are exciting from ground state to first higher excited state. So if I consider J is equal to J plus 1, and what I will here is, I have a value that is J dash minus J double dash. That is here J dash minus J double dash is equal to 1. So J is equal to plus 1 means that these terms is equal to plus 1. So here I can write it as J dash is equal to J double dash plus 1. J dash is equal to J double dash plus 1. Now I will substitute the value of J dash in our equation number 2. I will substitute the value of this J in this equation. Then what will be delta E is, then this is equal to omega naught bar plus B J dash minus J double dash. I will write J dash plus 1 in place of J dash. So J dash plus 1 minus J double dash into J dash plus J double dash plus 1. So further solving this equation, what we will get is this J dash plus double dash is plus and J dash double dash is minus. We can cancel these two and the equation will become omega naught bar plus here B into this B plus 1, and here is our 2. Here is I think here we have done some mistake. So here again we can write this J double dash plus 1 in place of this J. So the equation will be here we have 1. So we just let B into 1 is B, and we will expand this side and we'll substitute J dash is equal to J double dash plus 1 plus J double dash plus 1. So we have expanded both sides So the equation will be equal to now this omega naught bar plus b j double dash plus j double dash. This will be 2j double dash plus 1 and plus 1. This will be equal to plus 2. So I can further write it is, I will take b as common, then we see 2b j double dash plus 2 double dash plus 1. So this is our equation number third. So in first case, what we have done here is we have substituted J, that is deflection rule, for our rotational diatomic molecule, which is equal to J is equal to plus minus 1. So in our case second, what I will do is I will consider delta J is equal to minus 1. That is, our molecule is returning from higher state to our lower state. So this is our V is equal to 0, this is equal to V is equal to 1, this is our lower J, and this is our upper energy level. Minus J means that our molecule is returning from our higher state to our lower state, and there is change by only one number. It means it is allow it according to the selection rule. So delta J is equal to minus 1 means I will consider J dash minus J double dash is equal to 1. And what I will do is I will take the value of J double dash, and it will be your J dash plus 1. J dash plus 1. Now again, I will substitute the value in equation number 2, which is delta E is equal to omega naught bar plus B. In place of this J dash minus J double dash, I will write here J dash minus, in place of J double dash, I will write J dash minus J dash minus 1. Here it is minus. So again, our second term, that is the J dash plus J double dash minus 1. In place of J double dash, I will write J dash minus 1, and it is plus 1. Just write me plus 1 and plus 1 again. Here it is plus 1. So further, upon further solving, we have this delta J dash plus and J dash minus. So we can cancel these two. What will remain here is omega naught bar plus B into 1. It will be B, and again this is minus 1. Minus B omega naught bar minus B J dash into J dash. It will be 2J dash plus 2. So the equation will become omega naught bar minus 2, we are taking common, J dash plus 1. So this is our equation number 4. So we have two equations. One is delta E is equal to omega naught bar 2B J double dash plus 1. And the second equation is delta E is equal to omega naught bar minus 2B J dash plus 1. So when we combine these two equations, equation number 3 and equation number 4, so I can write here is these two expressions may conveniently be combined into, or I can combine these two equations and I can write delta E J V, that is the both rotational and vibrational, is equal to mu bar spectrum, that is our wavelength, omega naught minus 2bm. What I am doing here is I am replacing J dash plus 1 and our J dash plus 1 and J double dash plus 1 with our m. A new term I am introducing here is m. Now, what we mean by this m is the new term. This m is equal to, it can have value plus minus 1, plus minus 2, and so on. So we have another equation, equation number 5, where our m is replacing J double dash in our equation number 3 and J dash plus 1 in our equation number 4. And this m has values, I can say this m has positive values positive values when j is equal to +1, and this m has negative value when delta j is equal to -1. But this m cannot be 0. आपका m का value जो है 0 नहीं हो सकता. This delta m will not be equal to 0, since this would implies the value of j dash and j double dash to be -1. अगर आपका m 0 होंगे तो दोनों डेल्टा j +1 और डेल्टा j -1 दोनों का वैल्यू माइनस में चले जाएंगे. So this is not our selection rule. Our selection rule permits delta j is equal to +-1. So this m can have positive value for delta j is equal to +1, and this m can have negative value for delta j is equal to -1. And our omega naught bar, we have substituted omega -2 omega xe to xe with your omega naught bar, and this omega naught bar is usually called is band origin or band center. इसको हम बैंड ओरिजिन और बैंड सेंटर कहते हैं, जहां से आपका बैंड का ओरिजिनेट होना स्टार्ट होता है इन योर वाइब्रेशनल एंड रोटेशनल स्पेक्ट्रम. Our equation number 5, that is delta Ej mu or mu bar spectrum is equal to omega naught bar minus 2bm. The equation number 5 represents the combined vibration rotation spectrum. So this equation, that is equation number 5, will give you a combined vibration and rotation spectrum of a diatomic molecule. So this is equation. This equation is very important, where you can easily get the vibration rotation spectrum of a molecule. Evidently, it will consist of equally spaced lines. In the spectrum, the spacing between the respective lines are equal. Means if these are the lines, spectrum lines, then the spacing between the respective lines are equal, and it is equal to our 2b, is what we have seen our rotational spectrum. So on each side of the band origin means the omega naught value, where the band starts originating. But we know that the m is not equal to 0. The line at actual position of omega naught itself will not appear. So if we can draw the spectrum of a vibration rotation spectrum of a molecule, then we have a spectrum where the band origin starts at, for example, is if this is the band origin and its value were given by your omega naught bar, the line at omega naught bar itself will not appear, and correspondingly to the negative m value, that is towards lower frequency, this side, that is delta m is equal to minus, that is negative, and on the right side your delta m value will be positive. This side, that is this is equal to delta j is equal to -1, and this side delta j is equal to +1. The value of both -1 and +1 appear on the spectrum starting from our band origin or band center, where on the left side the frequency will we can say the frequency will be lower, and on the right side the frequency will be higher. But the value corresponding to delta m negative, or I can say delta j is equal to -1, the lines, this kind of lines, or the line towards the left of our band origin or band center, is known as our P branches. And the line on the right side of our band origin, that means the m is positive. M is positive means the value of delta j is positive. That bands are known as R branches, are branches. So in the actual spectrum, you will get different lines on both sides of the spectrum like this. The spacing between the respective lines are equal to 2b, and it remains constant. So these kind of lines you can get in the spectrum, in the actual vibration rotational spectrum, and the lines towards this minus negative delta m, or I can say where the value of delta j is minus, these branches are known as p branches. And towards the right side of our band origin, these branches are called as R branches. And the respective gap between these two lines are equal to 2b. And the first and the second P and R branches gap is equal to 2b and 2b. This will be equal to 4b. So this is how an actual vibration rotation spectrum of a molecule can exist. Now let's draw a energy level diagram of our rotational vibrational level and see how your spectrum can arises from that line. So we have vibrational energy levels. These two I am representing V is equal to 0, and the second vibrational energy level is this. This will represent the V is equal to 1. So this is the ground state and this is the first excited state. And we have number of rotational lines in between your vibrational lines, but the vibrational lines, the gap between the rotational lines are increasing as the rotational quantum number increases. So this is how we can represent a rotational and vibrational energy levels. This is represented by J dash and this is represented by J double dash 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, and so on. So we can easily draw draw the spectrum here. The spectrum will originate starting from our band origin or band center. That is the value is corresponds to our somewhere here is your omega naught bar, and from here the spectrum start rising, and on the right side you will get the R branches and on the left side you will get the B branches. So let's draw the spectrum here from the center of this band origin. On the left side, we have P branches, that is delta J is equal to -1. And on the right side, delta J is equal to +1. So from here, your first transaction can occur. And from here, the delta J 0 to delta J is equal to 1. So from here, ground state 0 to first excited state, you will get 1 peak. And from 1 to, you will get here from this J is equal to 1 to J is equal to 2. We can draw this like, and J is equal to 2 to J is equal to 3. So this kind of spectrum you can get. Again, on the this side also, you will get one spectrum from 1 to 2 because J is -1, and from 2 to 3. And this kind of change in the value of delta J is, it should be either +1 or -1. So in the spectrum, here is your band origin, that is omega naught, and here your right side is, we can draw it is R0, R1, R2, R3, R4, and so on. On the left side, you have P0, then we have P1, P2, P3, P4, and so on. So this side you will get the P branches, on the right side you will get the R branches, and the gap between the respective energy levels are 2B. This between these two is 2B, and between these two is 2B. So the gap between your R naught and P naught is 4B, because the line at our band origin center will not arise due to the condition that delta M should not be equal to 0. So this is how we can get the vibrational rotational spectrum of a rotating vibrating diatomic molecule. So this is how the rotational vibrational spectrum of a diatomic molecule we can get. Now, if we include the centrifugal distortion constant D, if we include the centrifugal distortion D. So in the starting, we have said that let's don't consider this centrifugal distortion constant because the value of this D is very negligible. So we have neglected it so that the equation will not become that much completed. However, if you include this centrifugal distortion constant, the energy will be given by your omega naught minus 2bm. So this is the equation which we got. So what we have to do is we have to add our 4dm3, that is our centrifugal distortion constant. On the value of m here is again m is equal to plus minus 1, plus minus 2, plus minus 3, and so on. And if you have and so this is the equation where we have included the centrifugal distortion, which is the actual case of a diatomic molecule, or we can say non-rigid diatomic molecule. In case of rigid diatomic molecule, you don't have to include this D, but we know that the real molecules are always elastic. So if you want to consider the centrifugal distortion, then you have to add this D term in this equation. Since we know that D is very small or very negligible, so we can neglect this D to a very high accuracy. Even if you don't include this D value, the value of your energy will almost be equal to what we can get after including this D. Although there will be slight difference, but the value will not differ that much. However, we have another term, that is our enharmonicity constant, but we have not excluded that enharmonicity constant, that is our Xe. Xe we have already included in our equation. What we have not excluded this Xe because we know that the value of this Xe, that is the square V plus half square omega E Xe, and we know that the value of this Xe term increases a square, which means the value of this total term will increase with increasing the value of your vibrational quantum number. That is, when your value of V increases from 0, 1, 2, 3, 4, 5, and so on. So at higher value, the value increases as the square of your vibrational quantum number, due to which we cannot exclude this Xe. So our omega E bar will be equal to, we have written this as this omega naught bar is equal to omega E into 1 minus 2 Xe. So our band origin, that is omega naught bar, is equal to our omega E, that is the vibrational frequency of enharmonic oscillator, into 1 minus 2 Xe, that is our enharmonicity constant. So if you have to calculate this omega naught, that is the band center, you have to include this Xe, because we know that at higher value of your vibrational quantum number, this will increase as the square of the second term. So this Xe not only affect the position of your band origin, not only position of this particular omega naught bar, but by extending. And the second point here is to note that if you extend the selection rule, where delta mu is equal to plus minus 2, plus minus 3, and so on, etc. The value of this Xe allows the appearance of Overtone bands having identical rotational spectrum. So the overtone, which we have said that at higher temperature, the transition from first energy levels can also occur to the respective higher energy levels. So in that cases, you can get some overtone bands also. So that's why we cannot neglect this enharmonicity constant. Now let's see the actual spectrum of vibrating rotating diatomic molecules. Then you will know what kind of spectrum you can get from a vibrating diatomic molecule. So this is the spectrum of your carbon dioxide. So This is the actual spectrum of your CO, carbon monoxide. So this is the actual vibrating, rotating spectra of a diatomic molecules, that is carbon monoxide. And you will see here that how these spectrum are appearing. So this is the actual spectrum, that is vibrating, rotating spectrum of a carbon monoxide. And in this, we can see that the fundamental starting absorptions were somewhere here at around 2143 centimeter inverse. And from here, the right side are our R branches, and on the left side it is our P branches. So these are, however, the actual spectrum arises, or we can say the rotating vibrating spectrum of a diatomic molecule arises. And along with this, here we have seen that what we have not neglected, the enharmonicity constant, that sometimes the overtones are also appeared. So here these are the overtone bands. Overtone bands means that instead of V is equal to 0, the transactions are starting from V is equal to 1 to higher energy levels. And these are the overtone bands, and it started arising somewhere 4260 centimeter inverse. So that's why the importance of enharmonicity is here, that at higher values, some overtone bands can also get. Now, if you magnify this spectrum to higher resolution, you will see this kind of spectrum. Where these are the actual our band origin, somewhere 2143 centimeter inverse, and on the right side how your R branches appear, that is R0, R1, R2, R3, R4, and so on. On the left side, your P branches arises P0, P1, P2, P3, and how these branches are showing, and the gap between the respective branches are equal, and it is equal to 2B. And the first gap between your P0 and R0, the gap between these two are 4B, because the gap between these two are 4B, because we know that the line at the actual band center origin omega naught will not appear, due to which we can consider the gap between our first P branches and the first R branch is equal to your 4B. And if you see this spectrum at lower resolution, you will get this kind of spectrum. अगर आपकी स्पेक्ट्रोमीटर का resolution कम होंगे, तो आपका P branches और R branches अलग दिखाई नहीं देंगे. आपको ऐसा कुछ स्पेक्ट्रम मिलेंगे जिसमें आपको एक कंबाइंड पीक मिलेंगे, कि इसके अंदर आपका बहुत सारे P branches होंगे और इसके अंदर आपके R branches होंगे. So this will represent your P branches and this will represent your R branches. अगर आपका मैग्निफिकेशन या resolution अच्छा होगा, then the spectrum will clearly get like this, where your clearly R branches and P branches are visible. This spectrum I have taken from the Benewell book, where you can see that the actual how beautifully the P branches and the R branches appear in the vibration rotation spectrum of a diatomic molecule. So this is all about our vibrating rotating diatomic molecule, or we can say vibrational rotational spectrum of a diatomic molecule. So that's all about our vibrating rotating diatomic molecule, and that's all for today. Thank you.